Hi, my name is Shekhar Sharma and I belong to a village Junabai in the district Sambhal of Uttar Pradesh. I did my undergraduation from Banaras Hindu University, Varanasi in the year 2017 and my masters with research from the Tata Institute of Fundamental Research, Mumbai, with a specialization in condensed matter theory. The condensed matter theory is a subdomain of physics where we study about the various properties of materials like the superconductivity, which is a property to let the flow of electric current from the material without any loss of electrical energy. We study about the optical properties of materials, and there are other aspects also where we are interested in. Presently, I have been accepted for the doctoral program in the College of Liberal Arts and Sciences of Arizona State University and about to join it in the fall 2021 as a PhD student. First and foremost, I thank the Mahamana Innovative Technology and Welfare Society, the MITWS, to start this initiative to share the research experience of the researchers in a way that the audience from non-research field can also understand it. I should say it is a challenge for the researchers also to express their work in the words that the audience from non-research background can also understand it. But it is the responsibility of all of us also. I'm sure it will extend the horizon of all the listeners and make them interested to opt for research as their career option. And so, in a way, it is a way to spread an awareness in the research sector. So this is really a wonderful initiative. Through this platform, I want to share one of my research work that I did when I was a part of the condensed matter theory department of TIFR. This was the work that was done under the supervision of Professor Vikram Tripathi, the senior professor in the condensed matter theory department of Tata Institute of Fundamental Research. So what did I do in my MS? So let me say in a single line, I studied the impurity effects in the Cative system that was perturbed with the Heisenberg interaction. I'm sorry if I have used too many technical terms in the previous sentence, but I will try to explain all in a as simpler way as I can. So let's come to the motivation of the work, because every work is done with a certain motivation. So what was the motivation of my work? So as we know that with the advent of computers in the human civilization, the exponential progress in almost every sector has been occurred. No area is there that has not been benefited by the usage of computers. And no need to say, the scientists and the researchers use the computers extensively to solve the problems that come in their way to understand the laws of nature, or in their way to study the systems that they are investigating. Computers help them to solve the problems at a very faster rate. However, as we have probed the nature deeper and deeper, more complications arise. Now we deal with the systems that range from very large sizes like the celestial bodies to a very smaller scale systems like the atoms and the electrons. The condensed matter theorists like me, they deal with the systems at the electronic level. It means at the size of the order of 10 raised to the power minus 15 meter, and they also deal with bodies that are in huge number, about the order of 10 raised to the power 23. Because even if you take a microscopically very smaller body like of the order of a micron, this body is also contains many particles. So it clearly implies that if we want to solve such systems, we do need to have extremely fast computers. Even the supercomputers, which are believed to be the fastest form of present-day computers, it is not possible to solve the problems exactly that deal with finite size systems. So what scientists are doing, they are trying to go one step further and working hard to create another class of computers that are believed to solve certain kinds of problems, not all, but certain kinds of problems at a very much faster rate with very small memory size. And these form of computers are called as the quantum computers. So what quantum computers will do? Quantum computers will tackle certain kinds of problems, and they will solve them with very faster pace. So it means if a certain problem is seems to be almost impossible to solve on a finite time scale, then the quantum computers can solve these problems in very short time. So in a way they will open up new domain where we can switch to study the systems. So how the quantum computers will do this? So quantum computers will work on a very simple law of quantum mechanics that is called as the superposition principle. So but what is a quantum mechanics? So quantum mechanics is a subject of physics where we study the dynamics of the system, or I should say the dynamics of the particles that are of the order of like angstrom, like of the atomic scales. So with now you can see that how the quantum computers can be useful, that with as simple as 10 particles, 10 spin-half particles, we will be able to harvest the work of about 2 to the power 10 bits, and that is quite remarkable. It means you just take the 10 spin-half particles, or these are named by a term that is called as the qubits, and by the usage of 10 qubits you will be able to harvest the work of 2 raised to the power 10 bits. Okay, so as we know the computers store information in the form of bits like zeros and 1, and they are called as the binary bits because there are just 2. So the systems, mainly the classical systems, can either be in a state 0 or in a 1, but not both at a given instant of time. However, the idea of quantum computers is to make the system to be in the superposition of both the states, that it can be in 0 and 1 simultaneously. And in the quantum mechanical language, these superposition are called as the qubits. So what is the main challenge? The main challenge is to look for the condensed matter systems that can host these qubits, that can show that this system shows the occurrence of these exotic particles called as qubits. There have been many systems predicted which are believed to host these particles that can be utilized as qubits, but each system has certain complications. So one of the system that also predicts to host these particles is basically the Cative system. It was given by a Russian physicist, Alexei Kitaev, and it is basically a two-dimensional system where we are having many spin-half particles, and these particles are interacting with each other with a certain kind of interaction. So this is also the system that I studied in my master's research work. And Cative system is an important system because it shows that we have the spin-half particles, and these particles that the Cative system predicts, they have the potential to be used for the quantum qubits fabrication. It means Cative system, we have the Cative system that is basically composed of many spin-half particles, and this system predicts the occurrence of certain quasi-particles, and these quasi-particles are believed to form the qubits. Now, what was my work? What did I do as my master's work? So by now you must have guessed that my work was also to look for the occurrence of such particles, but not in a purely Cative system, because Cative system is a theoretical concept. But what we need to have a system that should obey perfectly as the Cative model predicts. But we don't have any physical system that behaves exactly like the Cative model. So, but there do occur certain kinds of systems that obey the Cative physics, but up to certain limit. So it means there are systems that shows the Cative physics in addition of another physics that is called as the Heisenberg interaction. It means apart from the Cative interaction, we also have another kind of interaction that is called as the Heisenberg interaction, and that is basically the isotropic interaction. It means it doesn't depend upon the like it only depends upon the distance, not on the direction of the particles. So in that way, this interaction is called as the Heisenberg interaction. And what is the reason to study this specific system? Because the system is very close to many naturally occurring systems like the Na2IRO3 and alpha ruthenium chloride and many more. It means if one could able to see the occurrence of these quasi-particles in these more realistic systems, it will imply that we can use these systems to fabricate the qubits. So this was my as you can say that this is also the motivation to study this specific system. But now let's come to what was my result. What did I observe? Did I able to find out that this kind of particles occur, or the concept totally failed? So my result that I obtained after working for a year is that the system, which is the Cative perturbed with Heisenberg, do show the occurrence of these quasi-particles. But the problem is that these particles are highly vulnerable to the other perturbations in the system, like the stray magnetic fields that can in any way come to the system and destroy these particles. So it is like we have the particles, but we cannot have the ability to hold them. They combine with others and lost. So if we want to keep these particles so that we can use them to fabricate the qubits, we have to make our system or tune our system so that the particles don't mix with others. In the language of physics, we can say that we have to increase the Poisson gap of our system. So what methodology did I use? It means to get the result, what was the method did I use? So this work was mainly done computationally. It means we had to write a computer program that did our job. So in the work, I used Python and its libraries like NumPy. I also used a Python package called QSpin. This package is extensively used by the condensed matter theorists because it facilitates us to write down the Hamiltonian of our system in a very simple way due to its many already inbuilt libraries so that are specifically written to study the condensed matter systems. So I used the Python inbuilt libraries. I also used the QSpin package to study my system. Now let's come to the contribution and what is the importance of this work in the physics community. So the work that I did in the supervision of Professor Vikram Tripathi, it shows that the systems like the alpha ruthenium chloride and Na2IRO3 that do exist in nature can be potential materials that can be used for the quantum qubits fabrication, provided we can find some way to increase the Poisson gap so that the particles will be stable. It means if in near future this can be done, I think these materials will open a door towards the quantum computers fabrication, which I am sure will open a new paradigm. So let me put the pen to the hold by saying that research means direct connection with nature. Researchers work hard to understand the laws of nature so that these laws can be applied for the betterment of not only humans but everyone who is inhabitant of this beautiful planet. I know this is a tough time for everyone due to this pandemic, but I must say, don't give away your motivation to do creative in your life. Utilize the time wisely. Remember, the laws of gravitation was a result of the lockdown imposed in England due to the similar pandemic happened in Newton's time. So don't lose hope. Keep working. Things will get better. Keep learning and keep growing. I again want to thank the team of MITWS for giving me this wonderful opportunity to share my work on this platform. I hope I have done enough justice with the non-researchers also who are not related directly to this field.